It's been a long break in my lectures here. This final lecture here will only be about the upcoming written exam, which is in a week from now. As you can see, the time and place is already decided. It will be on Wednesday, 8 o'clock to 1 o'clock in Växjö. It should be in Stallvägen 10. Do you know where it is? On the other side of campus. Google it, you will find it. Or be there a bit in time. In Kalmar, it is at Västergård. I don't know where it is in Kalmar, but the Kalmar students, they know this. If you for some reason fail or you don't show up at the written exam, you have 2 more attempts this study year. We have a second attempt in November 26th and a third attempt in January 21st. This will be on Saturdays, and then the time is most likely 9, start at 9 o'clock. The exact time and place will be published in Moder, but this is the exact time and place for the upcoming one. Have you registered yourself for the exam? Yeah. Have you registered yourself? Online registration? Good. Anyway, the main purpose of having this is basically a programming course. I guess you have spent most of your time programming in this one. The main reason why we have this exam is that we must at one point in a course make sure that it's you and only you who solve the problem, not your gifted sister or someone else who helps you. So we have a written exam here, but it will be still programming. You have to write your programs with paper and pen. But the most important part here is to verify that it's you and only you who have done the exercises. Let's jump to the first one. This is pure Java. Write the program diamond that for an arbitrary positive and odd integer prints a diamond. So the program should work like this. It asks the user for a positive odd integer, and then it prints the corresponding diamond. You get the idea? My solution to it looks something like this. We are reading an integer. We have done that 100 times this course, so it should be in the backbone of you. We check if it is negative or even. In that case, we are printing an error message. Otherwise, we are printing the diamond down here. I'm iterating from 1, 3, 5 up to the width of the diamond, and then I'm calling the print method, and then I print the lower half. I'm iterating from n-2 down to 1, and then I'm printing the lower half down here. So the print method here, it takes the width of the diamond and the number of stars that should be presented in this particular line. Okay?
Excuse me.
Yeah.
You said you have to use pen and paper to write the code, right?
Yep.
You are expecting us to write the correct?
Let me present this one, and I can discuss paper and pen programming a bit later on. Yep. And this is the method I'm calling print. It takes the diamond width and the number of stars to be printed in this particular line. I'm building up my stars string here. I'm iterating over this one, and I'm just constructing n number of stars. If this is the width and this is the number of stars, then the white space size on both sides look like this. Do you agree with that? We have a line. It has the width n, and we have this many stars. The size of the white space here will then be n minus n divided by 2. You agree? So I just compute the number of white space here, and then I'm just constructing a string with this many white space here, and then I'm printing space plus stars plus space. Any problem with understanding the implementation? This is a typical first exercise in this course. Implement something. A few things that I would like you to prepare yourself with is that you must remember certain things. Static void main. I guess you're using Eclipse and they are generating this sequence for you. So remember certain things that you need to know about. But otherwise, of course, we understand that writing with paper and pen, you will do some errors. You might not remember all the string methods that are available or something like this. How do you pick out a character from a string? Charette. If you were writing just char, we would not kill you for that small mistake. So, but it should be Java and it should be a complete program. That means we are expecting, if we wanted to write a complete program, it should have a class declaration and a main declaration and things like this. My suggestion is you have plenty of time. You have 5 exercises for 5 hours. That means no one sits until spends all these 5 hours. So take your time, think and make sketches. And then once you know how to do it, you take a new paper and then you print it down properly. It's usually the best approach. Any questions? Other questions? Yeah, so we expect you to make tiny mistakes, but it should still look like Java. You shouldn't print line. We expect you to by now know that it's called system out print line. If you spell it with a lowercase letter here, it is okay, but if you just say put or something like this, then we think you haven't spent enough time with your Java exercises. So it should look like Java, it should be a complete program. And for example, if you are missing all the semicolons, then we think you are lazy. And then we remove a few points for you at all. It should look like Java. Questions? Oh. More Java exercises. This time we want you to write down a method. A public method is a static public method is palindrome that returns true if the string is a palindrome. We describe what we mean by a palindrome, and we also give you a few helping methods here that we think might be useful for you. And having these methods at hand, it is not difficult. Could you describe in words how you would solve this problem? I give you a string, you should check it if it's a palindrome. Ignore characters that are not letters and consider an uppercase letter to be equal to lowercase letter. The basic idea would be to
Put it in a loop for the length of the string and then...
Yeah, that's the second step, I would say. The first step is to clean it up in some way. I give you a string, this one. You go through it and you convert all uppercase to lowercase and you remove all non-letters in some way. Then you have a string of only lowercase letters. Then we do, as you said, we compare it back to forth or something like this. So this is the general approach. And this is exactly what I do here. This one here is the one where I'm converting it to a lowercase letter. I create a string builder to store my new string. I iterate over all the characters in the text, pick them up one at a time. If it is a letter, then I convert it to a lowercase and add it to my string builder. If it is not a letter, then it's a digit or question mark, we skip it. So after this step here, we should have, in our buffer, we should have a string containing only lowercase letters. Then it remains to do is to check whether it spells the same way backwards and forward. The simplest way is, The simplest way is just to reverse this, the content of the buffer, and ask if it's equal to this one. Otherwise, you can iterate over, you want to compare the first half with the second half, you iterate over half of it, you pick out the first character and the front character, and if they are not the same, then you can stop, then it's not a palindrome. So, different ways. Any problems?
They are both acceptable?
Both are acceptable, yep. Like when you solve an exercise in the assignments. If it looks okay and if it is correct, it's fine. The sorting method. Here we were rather vague. We said you should implement the method sort that takes an input array and returns a sorted version of itself, but it should not be the same array. It should be a copy that is sorted. You can sort it in any way you like. So, 2 steps. First, create a new array with the same elements. I create a new array with the same size as this one, and I move all the elements from in this array into this new array. Then I have a copy of it, a clone of it. And then I'm sorting this new array, and I choose the selection sort method here. And then I'm returning the new array. Read the exercises carefully.
Are we, for instance, in the previous example, allowed to use the sort method on correction?
Well, usually in this case we write you're not allowed to use any of the sorting routines in the Java library. Because in that case it would be too simple. So you can use everything from the Java library unless we especially point out that this one is not okay. Yeah.
All sorting algorithms, which algorithm is performed in which way, or
What?
do you want us to know all sorting algorithms?
I want you to know the selection sort, iteration sort, and merge sort, the basic ideas of them. Yeah. Which one is faster? Merge sort. Yep. Then you're perfectly okay. What was it more? Yeah. Read the exercise, read the text carefully. Creating and returning a new array. We want you not to sort the incoming array, you should make a clone of it and then sort this one in some sense. So you shouldn't ruin the input array by this. And ignore all characters that are not letters and consider. Read the exercise carefully and follow the instructions. If we don't give you any instructions, that basically means do whatever you want. Yeah. The third exercise. Now we move to data structures, but this is once again, we ask you to do a bit of Java programming here. We have given you a skeleton of a linked list. We are saying that there are 2 fields, size and head. So the list knows about the first node in the list. We are down here describing what we mean by a node, and you should implement add and remove. So we only want you to submit this method and that method. How do you add an element to a linked list? Yeah, you iterate to the tail and then you add it. And the only special case you have to take care of is...
No, empty.
Yeah, if it's empty, then you must add it as a head as well. Yeah. Remove, what was the strategy here?
The next one to the element.
Yeah, the before one in some way. You have... you want to remove this one, then you must actually locate this one and redirect this one like this. So remember the basic ideas and solve the programming problem when they appear. Add is straightforward. If head is null, that means we have an empty list. Then we are creating a new node and attach it to the head. Otherwise, that means we have one or more elements. Then we are iterating until the end of the list, until we find a node having the next pointer equals to 0. And in that case, we are adding it in the end of the list. This was one approach. What was the problem with this approach of implementing a linked list?
The big O of that and the big O, the performance of that.
Yeah, you made a what?
If we had tail, it was
Yeah. The problem here is that the add operator here actually works in linear time, ordo n. We had to go through the list every time and then add it in the end. So a simple way to improve it is to keep track of the head and the tail. Then we can jump directly to the tail and add it. So these are the two common versions of implementing it, or actually head is not common, it's a poor version, so no one is using it. Head and tail is the common approach. Remove. We are working with objects. So if, let's see here. Let's see what we are doing. If head is not null, okay. We must check whether we are about to remove the head node or not. So to remove the head node is a special case in this case. If the object is the same as the object stored in the head value, then we are bypassing the head and we are decreasing the size like this. If otherwise, find node before object, so we are iterating along the chain of nodes as long as the next is not null and we haven't found it. So we go through all the elements here and to show and look for it. If we find it, then this one will be false and we will stop. And in this case, the next pointer will not be null, then we are bypassing it in this way. If we don't find it before next will be null and we are not doing anything at all. Did you get the idea? Walk along this chain of node as long as we haven't reached the end of it or until we find it. If we find that the next value is the one we are looking for, then we are stopping, and then we should actually do this part down here. Yeah. Have you looked at exercises? Well, read this one. This is the X one, this is the Y one. And then she says that this one is ordo n2, and this is ordo n log n. Can Sally be right in her time estimate? We are measuring for the same size. One is faster, than the other, and they have these two time complexities. Has she done an error somewhere?
The time complexity is speaking about, I mean, when the n is going to
Infinity, very large. Yeah. So
they are not conflict between two results. Like,
can she be right or not?
she's right.
Yeah. 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 We think that this one is a faster one. It has a better time complexity than this one. So we might think that this one should always be faster. But this is actually not what a time complexity is. The time complexity tells us how they behave for a very large input size. So we might have the case that this one looks like this and this one looks like this. That is, for small sizes, 1000 might be small. This one might be slower. I think I've done it the wrong way here. Yeah. No.
Yeah, or and be going into until that.
Okay, yeah, fine.
It's faster.
So, time complexity only tells us how it behaves for some large n, and we don't know what is large n, but but if it gets large enough, it will be faster. So she might be right, although it looks contradictory that the one that is faster has the worst time complexity. It might be okay for small n. So what we want you to do here and say basically, Sally can be right, motivate your answer. A yes will not give you many points here. A no will give you 0 points. So the motivation is important. Sally can be right, and then I basically have written down what I just told you here. Do you understand the idea? What is topological order? A, B, C, D, E. I have a very small directed graph here containing 5 nodes. Give me a topological order. E, E,
Yeah.
C,
No, E.
G.
Yeah.
You're doing a post order.
Oh, what of them?
Completely wrong. It turns out to be. What is a topological order? A, C, no. A, B, C, D, E. Yeah. Think of the case of, my standard example are courses and prerequisites for courses. This arrow here says in order to read course B, you must have completed course A. And the question for topological order is, give me an order to read these courses in which way we are always fulfilling all the prerequisites. And you must start with A. Oh, oops, I should do it up here. You must start with A. It can B or C in any order. Then you must take both these courses before you can start this course. And of course, you must have completed D before you can start E. If you take a look at the definition that I presented at the lecture, it is a bit more mathematical. A topological order of a directed acyclic graph is an ordering of the nodes G in such a way that for every edge of G, U comes before V in the topological order. How does it correspond to what I suggest an ordering here, and you should check whether it's topological or not. Then you should take every edge here and see, does it point forward? If you find an edge that points backward, then you haven't found the topological order. So this is a more mathematical way of saying what I said earlier on. Yeah. Often we have a graph where the node corresponds to tasks to be performed, and an edge in the graph means that V is dependent on U. These are applications, and the only way to solve this task in the correct ordering is to do a topological order of them. And as I said, courses and prerequisites here. Yeah. I'll read up on this concept: topological order, post order, depth first search, breadth first search. You have just implemented it, so I thought you should be experts here in this one. How do you compute the topological order? Reverse post order, and it only works in one condition. Yeah. So for an acyclic graph, if you verify that it's acyclic first, then you can just compute post order and then take them in reverse post order, and it will give you magically a topological order. Write an algorithm in pseudocode or Java or anything close to that, which reverses a binary tree that mirrors it. How would you do that?
Using recursive function.
Well, yes, it should be recursive. Every time you have a tree, you should do it recursively. Otherwise, you will end up in trouble. So that's the first hint. Well, if I tell you like this, or yes?
We have to read it, and when we want to write new one, instead of putting the bigger one on each.
You should not copy it. You should take the existing tree and reverse it. It's actually simpler. But the basic idea is that you do a depth first search, and then in post order, when you return, you're just switching the place of them. Then you reach the leaves. You have a node here, and you have a node, two leaf nodes here, and this one is connected like this. You traverse the tree, and when you reach this point, you're switching the order of these ones. And when you reach this point, you're switching the order of these ones. And when you reach the top, the root node here, you have already reversed this one, you have already mirrored this one, then you're switching this one. So once you get the correct ID, it is done in 5 lines of code, basically, like this. Mirror left subtree, it should be mirror right subtree, of course, here, and then mirror this particular node, like this. It's an exercise in trees and recursion. Yeah. I do a depth first, post order. When I reach this one, I flip this two. And when I reach this one, I flip this two as well. It will be this one. Okay, let's move on. Formal languages. Did you see the lecture yesterday? Was it fun?
When we are going down,
Yeah.
for the left, for the left node, the leaf.
Yeah.
What happened for the left?
if node is not in the, when you're visiting the last node,
Yes, the last.
then from this one, or from this one,
Yes.
you would have said go and visit the left one, which is null.
Which one?
When you are in this node,
Okay.
and you are checking, is the current node not null? The current node is the leaf, so it's not null. So here you will say mirror node left, but this one will be null,
Okay.
and this one will also be null.
None.
So then we are calling mirror here with null, but then it will not do anything. The check here, if node not equal null, is the one that don't do anything for the leaves.
Okay, but okay, for that the left and the right, both of them is null for that.
Yeah,
And okay, they all flat. No problem.
good. Create a DFA that accepts languages with an even number of A's and B's. Here you should just sit and think, and then you should write it down. Yeah. I think for me it's obvious that we need 4 states. The first state is the starting state, in which case both A and B are we have an even number of them. So A even, B even. We have an even number of both of them. We have another state here where A is even but B is odd. We have a state over here in which A is odd and B is an even number. And over here we have that both of them are odd. These are the 3 different scenarios we have. Yeah. This is the one we are interested in. Both are even. So this is not only initial state, it is also the final state. What happens if we see an A? If we see an A, then we go from an even number to an odd number. A, if we are here and we see an A again, what happens then? Yeah. If you just decide that we have 4 different states in our system, then of course it's B here, it's A here, and it's B here. So if you see one A and one more B, then you are in this case. We have an odd number of them. And if you see one more of them, then you flips back in this or that direction. This was the way I was thinking when I solved the problem. But there is no recipe that works in all cases. But in general, you sit them down for a while and you sketch it, and you hopefully come up with something like this. There might be more solutions, I don't know, but this one works. So Q0 is both initial and final state in this case. Okay? Convert the automata below to a regular expression. This was actually the example I had on the lecture yesterday. At that time I was a bit rushed, so I didn't do it properly, so we can do it a bit more properly. How do you convert an finite automata back to a regular expression? Well, the idea was to remove one node at a time. in the end, you remove one, or let's start in another way. If you have a regular expression and want to do and construct an NFA, what was the approach? Then you had an initial state and you had a final state, and then you assumed you had your entire regular expression here. And then you divided the regular expression and added some components to it. Until the end you had reached one finite automata where we didn't have any regular expression. It was just single labels on all of them. Now we should basically do the same. We should try to take this one as our starting point, reverse, and go backwards and find something that looks something like this. So the idea here is this is the final initial state and this is the final state. We should remove these two nodes. And always start with a simpler one. This one looks a bit complicated, so let's start with this one. We remove this node, then we must replace things that this one makes possible in some way. This node makes it possible to go from Q3 to Q0 seeing 1 and 1. Yeah. So rather than having this node, we can add one edge from here to over here when we see 1, 1. And also this node makes it possible to go from Q3 to Q2 seeing 1 followed by 0. So we should say that you can go from this node to this node, not only on 1, but also on 1 and 0. I think I have it better here. This was the starting node. We would like to remove this one. This one makes it possible to go from Q3 to Q0 on 1, 1. So we are adding here, you can go from this one to this one seeing 1, 1. This one makes it possible to go from Q3 to Q1 seeing 1 and 0. So you can go from this one to this one by seeing 1, but you can also go by seeing 1 and 0. We are done eliminating Q2. Okay, remove this one. This one makes it possible to go from 0 to 3 by seeing 0 followed by any number of zeros followed by 0. So you can go from here to here by seeing 1, or take this longer approach here. Yes? Okay. This one also makes it possible to go like this. So going from Q3 to itself, you can do it by this option followed by any number of zeros followed by zeros. So I add a loop here saying I can go from Q3 to myself having seen this pattern. Now we are in a situation where we have the initial state and the final state. I clean it up a bit here. I say that it looks like this, U, V, and T up here, where U is this one, V is this one, and T is this one. Agree? Okay. How can I go from this to this? You must start with a U. And then once you have reached this one, you can do any numbers here or back or forth. Then you're still in the final state. So going from this one to this one using T, U, and V, I would say that you can go from initial to final by first seeing a U and then T, V, and U. You can do any number of T's and any number of V followed by U, going back and forth. Agree? So this is the result. You should then insert, it will be ugly. But this is the regular expression corresponding to this finite automata. It's the same way as going from a regular expression to an NFA. It is tedious, but if you just do it carefully, you should end up in the wrong way, in the correct, with the correct answer. Yeah, so remember the idea, try it on a few small cases, and then you're ready to handle all cases. It's just a matter of time then afterwards to handle them. A theoretical question or a finite automata, regular expression, and context-free grammar are examples of formalists that can describe languages. Rank them according to their expressive power. Which one is the most powerful one? And what do I mean by? If I can describe a language using one formalism, and I cannot do, this language is impossible to construct with this one. However, all languages I construct with this one can be handled by this one. Then this one is more powerful. It has a wider range of languages it can define. So, which one is the most powerful of them?
For regular languages.
What?
For regular languages, you mean?
No. All finite automata, regular expression, they all are ways to specify a language. There are 3 different ways to specify a language. Regular expression, we said that everything that matches this regular expression is a part of the language. Every string matches is a part of it. For finite automata, we said every string that is accepted by the finite automata, it's a part of the language. So they are all defining strings that are a part of the language. And for the context-free grammar, we said every string that can be derived using this context-free grammar is a part of the language. So they are all different ways of defining a language. Yes?
I believe the most powerful is a context-free grammar.
It's the most yeah. Can you give me an example of a language that can be described by context-free grammars and not described by regular expressions?
Some arithmetic expressions.
Some mathematical expression, it's a bit vague. Yeah.
They're all equal in power.
What?
They all equal in power.
No. This one is more example. The language with any number of A's followed by exactly the same number of B's. This one can easily be described by a context-free grammar. It's like this. It will generate number of A's and the same number of B's, and we can stop it at any time. But it's impossible to do it with a regular language. The problem here is that we have no upper boundary. Imagine an automata that looks like this. With A, I go over here. With B, I go over here. And this is not their initial and final state. With A, I go over here. And with B, I go over here. And I do it a long time. Then any number of A having the same number of B's will end up in this one. But this is not a finite automata. What is the problem?
The node should be limited. The node.
Yeah, finite. There are a number of them. You can do a very long sequence here with 2 million A's on top here. If I then give you a string with 2,000,001 A's starting here, then it will not work. So finite automatas and regular expressions, they are the same, they are equivalent. But certain things that you can do with context-free grammars cannot be done. And they often have this problem that they are finite in some way. Finite number of states. Yeah. So This one and this one, they are equivalent. In the lecture yesterday, I said for every every regular expression, there is a finite automata and vice versa. For every NFA, there is a DFA also. So they are excellent. And you can convert from one to the other. They are equivalent, but this one is more powerful. It can handle more constructs. And the simplest example to remember is this one. So the language, the mathematical language, as you said. This is my way of describing this language. Any number of A followed by the same number of B's in here. I also had an example yesterday with matching brackets. It's the same. You can do it, you can make it work with regular expression, but not for any number of initial brackets. Then it will run out of space. So this is the answer. And do you belong to the master program, all of you? Will you take the compiler course in next study period? You will be experts in this type of formalism, especially the context-free grammar. You will speak it fluently. Yeah. So that was 5 exercises. Was it difficult?
Not in the beginning, but yes.
Okay, the programming exercises was okay. But you haven't started to read up on the context-free grammars. No. It looks a bit strange, but like many things in computer science, you can look at an algorithm and it looks impossible. But once you understand the idea, it is not that difficult. Yeah.
Is there a video of yesterday's lecture?
Yes, I published this today after lunch somewhere. Yeah. Read the exercises carefully. As I said, we have certain restrictions. It should be an odd positive number. Then you should check if it's an odd positive number. What was it more? The sorted, you should return a new array, new sorted array. You should not sort the incoming array in the sort method. So read the exercises carefully. Answer the questions, nothing else. I will be the one correcting all these ones. And I will correct 50 of them. And if you start to answer other questions, I basically get angry because I will be tired. So read the question, answer it. Don't do anything else. We had a student a few years ago who said, I don't know this particular question, but this one I can answer. And then he gave his own question here, and he solved it perfectly on 2 pages. He didn't get much credit. Take it easy. You have plenty of time. 5 questions, 5 hours. It will be more than enough. So when it comes to paper and pen programming, do a few sketches, but when you feel comfortable with your solution, take a new paper. We have lots of forest in Sweden, so we have a lot of papers. So take a new paper and write it down neatly and correctly. For you, the Växjö students, I will show up after about 2 hours. So make sure at that time that you have read all the exercises and you understand them so you don't have any questions. So I will show up there and you are asking me, should I interpret this in this way or that way? Then I will say, probably in that way. If you say, I can't solve this one, can you please help me? Then I will say no, in that case. But you can always try. If you run into problems and there is no teacher available, and this is important for the remote students and those students in Kalmar, because they will not have any visiting teacher. Explain your problem in paper, make an assumption and continue. I'm not sure whether I should interpret this as so and so. I think this is the most correct one, so I stick to this one. But explain your problem and choose one of them and go on. Any questions? You have 1 week. I suggest that you spend a bit of time on the formal, regular expressions and context-free grammars. There will be a question related to one of these. Yeah, that's basically it. And read up. Rethink what you read through the slides one more time. Yeah.
About each, they have 5 questions. And
Yep.
they are from different areas. Will there be same
Areas.
score to each?
Yeah, I usually have 5 questions with 10 points each. They might contain 2 sub-questions and 3 sub-questions, but 5 questions totaling 10 points for each question. So you can have 50 as a maximum. To pass, you should have 25, and to have A or B, you should have 75%. That means 37.5. Yeah. Anything else? Yeah.
For the exam, about assignment.
Let's take it after this lecture. Yep. Okay, good luck. See you in the next course then, many of you. Bye.
Thank you.